Hello, everyone. This is Riccardo Calaon, and today I'm going to be presenting my paper, Solar Electric Propulsion GN&C Pointing State Overview for the Emirates mission to the asteroid belt. And before diving into it, I would like to give a quick overview of the EMA mission and define some of the requirements that characterize this mission. The EMA mission will launch in 2028, and it'll be the first mission to the asteroid belt. It'll perform flybys of the asteroids Westerwolde, Chimera, and Rockox, and some other asteroids that haven't been named yet. Ultimately, the mission will arrive at asteroid Justitia in October 2034. And some of the main features of the spacecraft, at least from a attitude GN&C standpoint, are the set of 4 reaction wheels, which are the main actuator for the spacecraft hub, 2 single-axis rotating solar arrays, and 2 dual gimbaled solar electric propulsion thrusters. Now, the SEP thrusters enable significant mass savings, but they also come with tight requirements, mostly because the SEP thrusters need to be active for very long periods of time, and having them active significantly affects the attitude in the sense that the thruster needs to be aligned with inertial thrust requested thrust vectors, which come from trajectory optimization. Another requirement on the attitude is posed by the 2 single-axis rotating solar arrays, for which the power generating surface of the arrays needs to be pointing at the sun at all times to generate enough power to keep the thrusters working. On top of that, with the solar arrays being so large, the spacecraft is significantly subject to solar radiation pressure, which ultimately would affect the attitude if it wasn't for the set of reaction wheels that can be spun up and down to absorb the momentum being imparted on the spacecraft. All these challenges lead to the definition of a SEP pointing state, which is the main guidance, navigation, and control state for the EMA mission during the time when the SEP thrusters are being active. So let's define the 4 main requirements for the SEP point state. Requirement number 1, the spacecraft shall control the SEP dV thrust vector during SEP operations to be within 1 degree 3 sigma radially about the thrust vector. This requirement describes the fact that the thrust vector needs to be aligned with the inertial request, which comes from trajectory optimization. Number 2, the spacecraft shall control the solar array normals to point towards the sun to within 5 degrees 3 sigma during SEP operations. This comes from power requirements, and this means that the solar arrays need to be facing the sun at all times while the SEP thrusters are on. Requirement number 3, the spacecraft shall minimize the angle between the spacecraft body frame plus y-axis and the sun direction when completing SEP delta V maneuvers in a commanded inertial direction. This is the less intuitive requirement, and it stems from the fact that there is a thermal sensitive surface in the negative y axis of the spacecraft. Therefore, we want to do our best to maintain this surface in the shade to avoid overheating of the spacecraft. And number 4, the spacecraft shall control the buildup of momentum such that reaction wheel desaturation is required no more than 1 time per 7 days. Specifically, this means that we are performing desaturation maneuvers using thrusters only once every 7 days. Now, all these requirements make sense if considered individually, but given this description is not sufficient to fully understand the complexity of the problem that we need to face. So to make this whole set point state more digestible, in the next few slides, I'm going to present a block diagram that shows all the functionalities that the set point algorithm is supposed to solve for, and hopefully dividing them into smaller functionality bites will make them more digestible. Now, functionality number 1, nominally point the SEP thruster through current spacecraft center of mass. Keep in mind that this is a first cut in which we assume to fire the thruster through the center of mass of the spacecraft because we want to avoid injecting more momentum onto the spacecraft, which would have to be compensated by the reaction wheel. Therefore, the only input to the set point algorithm here is the center of mass location of the spacecraft. And the set point algorithm is able to compute a reference body frame direction for the thrust vector. This direction is passed on to the SEP gimbals, which can be controlled in order to fire the thruster through the center of mass. Now, functionalities number 2, 3, and 4, and we will get in a moment into why these three are lumped together. Functionality number 2, maneuver the spacecraft to align the SEP thrust vector with the requested thrust direction. Functionality number 3, rotate the spacecraft about the thrust direction to get the solar array drive assembly rotation axis orthogonal to the sun and point -y as far away from the sun as possible. Functionality number 4, rotate the solar arrays to align array normals to the sun direction. The only inputs to the set point algorithm here are the inertial SEP thrust direction command, which once again comes from trajectory optimization, and the direction of the sun. These pieces of information are fed to the set point algorithm, and the reason why we lump these functionalities together is that they are all solved for by defining the optimal reference frame for the spacecraft hub such that all those three requirements are satisfied simultaneously. As we can see, once the attitude reference is generated, it's passed on to the attitude control subsystem, which is updated at 10 Hertz. And the controls generated are passed to the reaction wheels to actuate the spacecraft. Functionality number 5, it's the autonomous momentum management with the SEP thruster. So this is a variation on the functionality number 1 discussed before. Here, the input to the set point algorithm is the explorer momentum, which is fed back from the reaction wheel states. It goes into the autonomous momentum management algorithm, which computes an offset with respect to the center of mass location estimate. So once we receive the center of mass location estimate, we add an offset to it with the objective of not firing the thruster through the center of mass of the spacecraft anymore, but firing it at an offset which is defined in order for the thruster to bring down the momentum that's accumulating on the reaction wheels. Therefore, we are strategically using the gimbals not to not generate a torque on the spacecraft, but to generate a torque that can continuously manage the momentum building up on the spacecraft. Functionality number 6 is not really a functionality, is more of a requirement that we need to embed into the set point algorithm. And it's given by the fact that we have two SEP thrusters. Therefore, there needs to be a logic in there that informs the algorithm about which thruster is being used and the location of the thruster with respect to the center of mass. And now let's get into the mathy part. Here, I'm going to be describing the guidance and control algorithms that are used to generate references and control all these parts of the EMA spacecraft, specifically the SEP thruster gimbals, the attitude of the hub of the spacecraft, and the solar arrays. Starting from the first one, the thrust vector T is applied through the dual gimbal, whose frame F rotates with respect to the body frame B. The gimbal can only perform compliant 2 degrees of freedom tip and tilt rotations of angles nu1 and nu2. And there is a closed form solution to compute the reference angles nu1 and nu2 that such that the resulting direction cosine matrix that maps frame B onto frame F makes sure that the thrust vector is aligned with a certain point in the spacecraft. In this case, we can assume that this point is the center of mass of the spacecraft. In this drawing, we see only one thruster, but this math can be easily generalized to a case with multiple thrusters. Now, there is, like we said, a closed form solution to align the thruster through the center of mass. But here we really want to implement the strategy to make sure that we are continuously managing the momentum building up on the spacecraft. Therefore, we need to define a term H, which consists of the net momentum on the spacecraft. And then we define an offset vector D, which describes the offset at which we want to fire the thruster in order for the resulting momentum the resulting torque to bring down the momentum on the spacecraft. This offset vector D is defined using vector math, and it's ultimately proportional to the net momentum on the wheels. This means that the larger the momentum on the wheels, the larger this offset with respect of the center of mass is going to be. And there is a proportional gain kappa, which has the dimension of hertz, which is a tuning parameter for this guidance law. Now, it is also important to define or to add into this guidance law an integral term that feeds back on the integral of the net momentum. This is done because the location of the center of mass is often known within certain accuracies. So adding this integral feedback term compensates for these inaccuracies and makes sure that over time, errors in the center of mass estimate are being compensated for. As far as how to actuate the gimbals, currently the current design simply implements some PD controllers that zero the error between the current gimbal angles and the desired gimbal angles. Switching over to the attitude guidance law, attitude is a three-dimensional problem, and this attitude reference generation problem is particularly interesting because we have multiple constraints that we need to solve for. Number one, the body heading. There's a body heading that needs to be aligned with an inertial reference heading. In this case, this reference heading is given by the thrust vector in body frame coordinates and the requested thrust direction vector in inertial frame coordinates. Requirement number two is to drive the solar array axis to be orthogonal to the sun. And number three, to keep the thermally sensitive surface direction away from the sun. Now, the first requirement locks in 2 degrees of freedom, and the second requirement locks in 1 degree of freedom. So in general, this problem is overly prescribed. Therefore, there can be too many constraints and not enough variables to solve for. Even more so when we add a third constraint. So it is important to define a list of priorities in which we want to try to enforce these constraints. So number one is, well, the first priority is priority number one. Therefore, we always want to align the thruster with the inertial request. And this is always possible when considering this requirement on its own. Now, enforcing the second requirement is a more interesting problem. Once the thruster is aligned along the required direction, it is possible to roll about this direction in order to minimize or to make sure that the solar array drive axis is as orthogonal as possible to the sun line. This can be done in a smart way by using an attitude parameterization given by the CRP's classic Rodriguez parameters, also known as Gibbs vector. Doing so transforms the problem into a quadratic equation for which there is known solution. This quadratic equation has 3 coefficients, a, b, and c, that are functions of known parameters. So ultimately, we are simply solving a second order equation, which is very simple. However, it comes with caveats, which are the fact that if the delta or the discriminant of the second order equation is positive, there are in fact 2 solutions for which the first and second constraints can be enforced simultaneously. However, if the delta is negative, there is no solution to this problem, and we need to implement a constraint minimization solution. Now, given the design of the spacecraft, this design is quite benign, and it can be shown that the characteristic equation almost always has a positive discriminant. Therefore, we always have 2 solutions. And the positive thing about having 2 solutions is that we can also choose whichever of the 2 makes sure that the thermal sensitive surface is kept away from the sun, or as far away from the sun as possible. Once the ideal reference frame is computed, it is passed to the attitude control law, which is a nonlinear PID-like controller. This controller, there's nothing new about it. It can be found in Schaub and Junkins. Effectively, it's composed of 2 parts. The first part of the controller on the first line is the real proportional integral derivative terms, whereas all the terms on the second line are gyroscopics that are added to the control law to ensure that it's globally asymptotically stable. It's worth noting that the inertia of the spacecraft, which appears in the control law, is a term that changes over time due to the moving parts of the spacecraft. However, it can be shown that within the assumptions that can be made for this problem, such as the reference frame not changing very quickly over time and the spacecraft being in an almost static configuration, the second line of the control law becomes negligible compared to the first line. Therefore, all the inaccuracies in this model become uh, not very relevant in terms of the control implemented. Also, the integral term is particularly important for this simulation for this mission in the case that there's an offset of the thruster with respect to the center of mass, because when this happens, the resulting torque on the system is exactly a constant unmodeled torque, which is the type of torque that can exactly be compensated for by the integral term in Z. Um, Moving on to the solar array guidance law, this can be computed very easily. Um, we simply need to know the direction of the solar array drive axis in the reference frame and the solar array drive axis in the body frame and the direction of the sun in that body frame. And we compute a reference orthogonal direction as a linear combination of the two, from which it is possible to compute the rotation angle that we need to rotate the solar arrays by to ensure that the power generating surface of the arrays are facing the sun. In terms of controls, the solar array drive assemblies are actuated via stepper motors. Therefore, whenever the reference is given to the arrays, these controllers take finite discrete steps towards the commanded angle. However, these are not very relevant from a GN&C perspective, so he will not get into the details of that in this presentation. And let's get to the simulated performance of all these components. And once again, let's start from the set gimbals. Now, in the plot on the left, we can see the commanded angles and the performance of the gimbal angles. We can see that the angles are tracking the references very quickly. This is important because the gimbals are actuated every hour, and so we want the gimbal angles to track the references in a very short time compared to the 1 hour frequency for the gimbal references. On the right, we see the offset between the thrust vector and the center of mass. It looks like it's dropping to 0, but it really isn't dropping to 0. It's dropping to 0.3 degrees. This is because when the system reaches steady state, this 0.3 degree offset is what ensures that the thruster torque acting on the spacecraft counterbalances the action of external forces and torques such as SRP. Talking about the attitude, the plot on the left shows the error between the body frame and the reference frame, and we can see that this error is dropping to 0 over time as it would be expected. More important is the plot on the right, which shows the pointing accuracy of the thruster. And we can see that as the spacecraft slews to attitude, the error between the thrust direction and the commanded thrust direction is dropping to 0. As far as the solar arrays, we can see that when the references come in, the solar array angles quickly track those references. It looks like the performance is linear. It isn't in fact linear. If we could zoom in on the plot on the left, we would see that the solar arrays are taking very tiny steps towards the reference, but from a macroscopic perspective, it looks like they are being actuated linearly. Most important is the plot on the right, once again, which shows the offset angle between the power generating surface of the arrays and the sun. And we can see that it drops to 0 initially when the solar arrays are being actuated, but then the final descent to 0 is obtained as the spacecraft slews to attitude. And final, this plot is shows the performance of the reaction wheels over the 7 days. And we can see that momentum is building up on the wheels due to the swirl torque of the SEP thrusters. Now, this torque is a byproduct of the SEP thrusters that are being used in this mission. And because this torque is collinear with the thrust direction, it is not possible for the momentum management algorithm to compensate for it. However, we can see that if the wheels are biased negatively at t equals to 0, we can accommodate the momentum buildup on the wheels to make sure that the wheel speeds stay within operational levels for 7 days. As opposed to that, all the torques acting on this system and orthogonal to the thrust line are being absorbed by the momentum management algorithms. So in conclusion, we're successful at simulating 7 days of spacecraft SEP performance without the need to ever perform momentum dumping. In conclusion, the Emirate mission to the asteroid belt presents a unique set of challenges for GN&C, particularly during periods of solar array propulsion thrusting. This paper outlines the challenges related to pointing constraints and momentum accumulation, the requirements on GN&C to execute SEP sufficiently, and the algorithm and state descriptions for the GN&C flight mode with the associated SEP pointing state. Simulation results show the execution of the GN&C set point state, giving confidence in the implementation, and future work will involve a thorough validation and verification process for the simulation models and flight software algorithms. And now, before saying goodbye, I would just like to show the simulated performance of the spacecraft. There is not much that can be observed in the simulation except for the solar arrays articulating to track sunlight, but if you pay close attention, you'll see that the spacecraft hub is also moving slightly. It is moving very little because we are starting this simulation very close to reference attitude. However, it is very interesting to visualize the performance of the spacecraft. And with that, I'll conclude this presentation and thank you all for paying attention.